let's have a look at an example which has two circles in the question. In this particular question, I'm giving you the equation of a circle, and I'm giving you a second equation of a different circle. And the question I'm asking you is, can you please prove that those two circles intersect externally at just one point? So they touch externally at just one point. So the situation is something like this. We have got to prove that that situation exists. Okay, and what I'm going to do is first of all tackle it a way that many students start off by doing in the examination, and they will get some credit for it, but they won't get full credit for it, as you'll see. What a lot of students do to try and show that these two circles intersect at a single point like so is they'll try and solve these two simultaneous equations. So they'll solve these two simultaneously. So, for example, if I call that number 1 and I call that one number 2, we might try the following. Now, as you can see, they're both quadratic, and we haven't done simultaneous equations where they're both quadratic. So sometimes trying this sort of thing can lead to sort of a situation which cause a lot of problems. But hopefully, fingers crossed, if you follow what I do now, you will see some of what follows makes sense. But like I said before, you won't get full credit for it. What I'm going to do is notice that in both of them, x squared plus y squared is present, x squared plus y squared. So what I'm going to do here for number 1 is show you that x squared plus y squared is the same as 2x plus 3. Okay, x squared plus y squared, leave it there, take the 2x and the 3 to the other side, you get plus 2x plus 3. For the other one over there, I'm going to do the same sort of thing. For number 2, I'm going to show you that x squared plus y squared is equal to, take the minus 8x over, you get plus 8x, plus 15 becomes minus 15. So for this circle, x squared plus y squared is equal to 2x plus 3. For this circle, x squared plus y squared equals 8x minus 15. So in this situation, because they're quadratic, I'm going to think on my feet a little, I'm going to adapt a little. I'm not going to use the same technique that I would use for one linear, one quadratic, where I get x or y on its own and sub in the x or y from the linear version into the quadratic. What I'm doing is rearranging them in that format. This one here tells you that x squared plus y squared is 2x plus 3. And this one here tells you that x squared plus y squared is equal to 8x minus 15. So it must be true for these two circles that x squared plus y squared at any intersecting point must have that 2x plus 3 must be equal to 8x plus 15. That must be a true statement for any point which lies on both circles. So we get that statement coming out, and as you can see, that statement there is an equation which is a linear equation, which means that there is only going to be one solution to this, and that one solution is the one intersection point which we're referring to. So if I wanted to find the actual point, I could actually solve it. So you get 8x minus 2x on the right, and you get 3 plus 15 on the left. So you get 18 is equal to 6x, share by 6, and there you go, you get 3 for the x value. Okay, and so that tells you basically that there is just one intersection point. Its x value is 3. Obviously, if I wanted to find the y coordinate to get the actual point itself, I would have to put 3 into say this second thing here, and I could work through, and hopefully that would be enough for me to be able to work out what the y value is. Really, I'm not interested, because there's a problem with this. Whilst it does show that there is one intersection point where those two circles meet, and it happens when x equals 3, it doesn't show, now if you remember what I said to you at the beginning of this question, it doesn't prove that they touch externally. So the two circles could be drawn like this. Either of those have one intersection point. The question I was asking you was specifically aimed at saying, show that those two given circles touched externally at one single point. So I cannot be sure using this technique which of those two pictures I have got. Because of that, I'm going to abandon the simultaneous equation method for this particular question, and I would recommend that you don't even start it if this was the exam. Okay? This is the procedure I would recommend that you follow, and it follows on from the theoretical work I did in the last video of two circles where we had 6 or 7 different scenarios to look at. So, if I go back to the beginning again, for each of these circles, what I'm going to do first of all is work out what the centre and what the radius of the circle is. So I'm going to use the techniques I've done in the past. I'm going to restructure x squared, then I'll put the minus 2x, then I'll put plus y squared, then I'll put the minus 3 onto the right hand side to make it plus 3. I'll then use completing the square on this, so you're going to get x minus 1 in a bracket squared, minus 1 being half of the minus 2. Square that, you get x squared. Multiply the 2 together and double, you get that. You also get a plus 1 when you square the minus 1. So that is excess to what we want. So to compensate, you take away that 1. So that is the same as that. Plus the y squared, I don't need to do anything at all with that. I can leave that alone. It's already a squared quantity. Equals 3. Let's restructure it. I'll put the bracket squared first, then I'll put the y squared next, take the minus 1 over, it becomes a plus 1, so you get a 4 on the right hand side. So we end up with that statement there, which is the bracket notation for this particular circle. Okay, I can see from this that the centre of the circle is therefore, if that's minus 1, it's going to be 1 comma, if that's just a y squared on its own, it's going to be 1 comma naught. And I can see that the radius is the square root of 4, the radius is 2. So I've found that information. Going to do the same sort of thing for the other circle now. So restructure it, put the x's first, x squared minus 8x, put the y squared next, take the 15 to the other side, like so. Okay, completing the square, x squared, sorry, means x there, minus 8x, you need a minus 4, put it in a bracket. Square the first, you get x squared, multiply the 2 together and double, you get minus 8x, but you'll also get from this a positive 16, which I don't want, because there's no positive 16 up here. So I need to take away 16. Now, that expression there is the same as that expression, x squared minus 8x. The plus y squared is already a squared quantity, similar to what it was over here, and equals minus 15 I'll leave alone. Okay, so reorder, I'll put the bracket squared again, plus y squared, and I'll take the minus 16 over to become a plus 16. Plus 16 with minus 15 gives you a positive 1 on the right hand side. Now it's in this format, I can write down that we've got centre, well, if that's minus 4, this must be plus 4. If that's just a y squared on its own, it must be naught. And radius will be the square root of 1, which is 1. So I've got 2 sets of information now for each circle. I know each specific centre, and I know each specific radius. Now, to prove that they touch at one point externally, let me remind you again with this picture. If I work out what the radius of the first one is, well, I know that, 2. And I know what the radius of the second one is, well, I know that one as well, 1. Then you can see that the radius of the 2 circles added together, R1 plus R2, will give you a total of 3. Okay? So, in this particular case, R1 plus R2 is equal to 3. Okay, if we have that setup. Now, if that setup is true for this particular pair of circles, then what I'm going to do now is work out the distance between the 2 centre points of the circles. If the distance turns out to be 3, then we must have that picture where the radius 2 plus that radius 1 must be side by side to give the total distance, which is 3. So the object of the exercise is now simply to work out the distance apart of the two centre points and prove that it's equal to 3, which is R1 plus R2. So this is what I'm going to do. I'm now going to take the two centre points, 1, 0 and 4, 0. I'm going to call that x1, y1. I'm going to call that x2, y2. I'm going to use coordinate geometry, distance between 2 points. Okay, so in the space here, the distance that I'm looking for is going to be the square root of x2 minus x1 squared plus y2 minus y1 squared. That's the coordinate geometry formula which was derived, if you remember, from Pythagoras. Okay, equals the square root of x2 is 4 minus x1 is 1 in a bracket squared plus y2 is nothing minus y1, that's also nothing, in a bracket, and you've got to square it. So you get the answer, the square root of 4 take away 1 is 3, which you've got to square, plus you've got nothing squared, which of course is the square root of 9, which is 3. So you can see that the distance between the two centre points is a distance of 3. And that was exactly the same distance as R1 plus R2 added together. And that is a condition for this situation. The two radii added together is equal to the distance apart of the two centre points. So therefore, the distance apart must be equal to R1 plus R2, the distance apart of the two centre points. So therefore, circles touch at one point externally. And of course, once you'd actually worked out the centre and the radius of both of these, it would be very simple for you to actually, I'm not going to do this, but it would be very simple to plot them accurately on a scale diagram, get a compass out and draw the things properly, and you would see you'd get that picture where the two circles would be touching in that fashion. Of course, as always, you wouldn't get full credit, or if in fact any marks, if you did it by a scale picture. You need to do it by these techniques. Okay, that's the end of that question.